Hi, my name is Eric Hollinsby. This is the Scarlett School, and the point of the Scarlett School is that there is technical education for everyone. We'll republish this as a video later, so if you're worried about missing the stream, no problem. It's 1 a.m. here, 1:30 actually, and I'm not surprised at all. Nobody will be watching this, but I'm just learning how to do this, and so I'm not in a big hurry to do it right. Today we're building the tomatrix program. And if you look at the code on the screen, that's kind of what we'll end up building. I'll show you what it does in a second. Um, the point of this show today is to demonstrate a moderately advanced program that we can do in a single session and show the concepts around the building of that program. What the program does is it creates a matrix display on the screen. So we look here and we're on tomatrix, which is already installed. We can install that with cargo install tomatrix with a URL for that, and the source repository are in the YouTube description. You see here we feed the input of the source code to this program as standard input, and then this happens. Um, Now you can see that there's quite a bit of activity going on, and it does it at a fair rate of speed. If you were to check the CPU usage, which is right here, we can see that most of the CPU usage is actually in Zellish, which we'll talk about in a minute. And the 2 matrix is actually only using 4% CPU of one core. Now, and that's because of all the activity on the screen. Let's see here. The environment. Let's talk about the environment for a minute. So what we use is Neovim. I'm using a PPA that uses the nightly builds. Um, Inside of Neovim, we have a number of Rust tools to help us work. See that we have auto completion through Rust Analyze. Um, we have syntax errors through Syntactic. You see, and that'll highlight all of that. Um, other little things like we don't actually use the anyhow macro in here, so it'll tell us about that. The terminal environment is Zellish and Kitty, um, and yeah, I mean that's a pretty basic thing. Um, yeah, and what we'll have here is I probably just did that. Anyway, what we have here is able to split the terminals. ZSH is used here. I use a custom config. Um, let's see what else. Yeah, that's about it about the environment. We're using Rust, obviously. We just picked up the latest version today, so that's 1.77.2. Um, Other than that, you should definitely know Rust in advance before we get into this. And the reason for that is that I'm not going to spend a lot of time explaining the typing system or explaining Rust intrinsics. Instead, I'm going to get right into the logic, try to explain the deeper concepts and how we got to this position. And yeah, outside of that, we'll get started, I guess. Yeah. All right, and we're back. So let's see here where we were. We were just talking about the Rust version, and now we're going to get into the project. So I'm going to make this code disappear. Um, and what we'll do is we will create cargo, which is our Rust kind of overall usage tool. We'll create a new package. We'll create it as a library package. Put matrix 2. And what tomatrix 2 will do is give us our skeleton in library form. And what we'll do is we'll fill out the library and then we'll create a second binary called tomatrix 2. And we can do that with that mkdir command. Instead of creating it as another way of doing this is to create main.rs right here in source. But the problem with that in this case is we can't keep the lib. So if we want to split out the code into a bunch of different places, we're actually kind of stuck and trapped in that source slash main.rs. So what I like to do is create one in bin, which will have the same exact effect, and give us that cargo run functionality. First, we need to edit dependencies. So we need two major dependencies in here. This one is for handling the terminal, cross-term. And I don't actually know the version of that. And until I publish uh, the crate, which we're not going to do, I don't need the exact version. So I just put a star here to pixelate it. In a similar vein, we know we need version 1.0 or later of anyhow, which is a library that helps us with error codes. Now, what we've done here is tell it anything greater than 1.0, which will pick the highest level version. So through this, we can try to build, we can get all this loaded up, right? And then we can go into source, and tomatrix2, and rs. Now we're going to create our main function, and we're going to do this. We're going to use anyhow result. Okay. And the advantage of using anyhow result here is that this result enum takes either an OK or an error. Each one has their own independent type. The error has an error style type, and the OK has the actual value that you want in the case there's no error. So I guess what I'm trying to say here is that anyhow's result type doesn't require an error type because they're all expected to be compatible with anyhow error, which is its own type. So what this allows us to do is kind of skip that extra error typing. And if we want an error, now as I mentioned, because we have one binary, cargo run now works. We don't need a main. So as you saw over there, we ran it. Now the thing is when an error comes back, and we're going to manufacture one with this anyhow macro, error, this will bubble up into the actual program. So you see that anytime we have an error here, we can output it to the user and it'll all just be obvious what happened. They like to read. Rust gives us features to bubble this error up all the way to the main function. We just have to use them right to have this behavior work for us. So let's start off on the right foot. Program does nothing right now, but it's in the right shape. So now that we're going into the actual meat of the program, we need to talk about what we're going to do. So fundamentally, we're going to take the input. We're going to basically create an array of characters out of it. And we could unique those, but it really, it's just more time. And the random selection is so fast that it doesn't really have a benefit other than for memory usage, which makes sense, but it's not really a big deal with this kind of a program, right? We need to draw the letters in the appropriate way, and we also need to make sure that the screen isn't overflowing with them, so it presents that kind of sparse look that we want in the matrix terminal output. We should be able to handle Unicode. We should be able to quickly determine how to do all this and draw it in a way that uses a minimal amount of work as possible, both for the program outputting the data and the terminal program ingesting the output of the terminal of the original program. So when the terminal needs to draw something on the screen, it just outputs that character until it needs to do something special with it, like change its color, or clear the screen, or move the cursor to a specific position. Right now, this allows us to output these codes so we can manage it, but they're actually a lot more than one character. If you look into the VT100 character set or the control set, which you can just type into Google, like VT100 escape command set. That'll probably get you exactly what you want. you can see that there are at least 3 characters just to move the cursor. Actually, it's more than that. It's something like 7. Um, and to move the cursor and then output something and then move the cursor again, which is what we're going to do, it's actually a lot more output than outputting the whole screen. There are some good arguments for doing either or. And with the way we're doing it, we should probably, clearing the screen would probably actually be better. But what we're going to do today is position because that's what I've already done. Uh, if you want to take this as an exercise unto yourself, the repository is there. You can try clearing the screen. That would be pretty cool. I'd love to see that patch. I think the first thing we need to start with is some predicates. Kind of figure out how our loops work. So we're going to have a draw loop, and this draw loop will, kind of control the timing of the whole frame rate of the thing. So it will draw a whole screen's worth of data and then pause and then draw a whole screen's worth of data again. Right? This is terminal IO 101. And then inside of that, we'll have an inner loop which actually outputs each individual character in its right position, right? Um, and how we do that will depend on how resource hungry it is. I think a big thing to consider here also is when we take the time to calculate cursor movement or character movement. So as the characters fall, right? Sometimes they change characters in the movie, and also they change colors like intensity, brightness, etc. Um, at the same time, they're falling at varying rates of speed. So they'll fall really fast and then fall really slow and then blah, 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 blah. But anyways, we want to simulate this whole kind of behavior because it really doesn't work unless you do. Also, there's not a ton of stuff on the screen. If we look at this, oh, oh, there we go. If we look at this, you can see that it presents a fairly convincing screen, but if you compare it to the matrix on the movie, like the bottom of the screen is generally way more untouched than this one. So there's a couple of flaws here, right? That's fundamentally what we want to avoid is introducing too many of them because, as we try to patch flaws, things will get more complicated. But as we acknowledge that some flaws are okay, we save time. That's a basic software engineering adage. So let's start by getting anyhow result. Okay, and let's create some predicate functions. I think this is really important towards, just getting the basics in there so that we know how probability is handled. So let's try. Okay, so we know that the letters are going to fall at a certain speed. So let's measure it in terms of cells on the screen. So if we look at this, what we can do is cat lines, right? Oh, echo lines. Sorry. And the shell will tell us how big our terminal is. So it is 50 lines long in this case. Go column, and that's 91 columns. Okay. So one thing that I could be doing better right now is moving this thing so it's out of the way of the video screen. But I haven't figured that out yet, so you're gonna have to wait. Anyway, so if we pick speed, and we bring in rand, we can random, and we can modulo this by the max speed, and what this will give us is something that's 0 to 3. Oh, I forgot to bring in rand. Let's do that now. Oh, yeah, that's gonna be bad. Okay, so unfortunate problem about our situation right here is that the type hinting is not, the type inference is really not working in the way we want. Um, and yeah, so I mean, we're going to kind of have to hint it and feed it some information. So for now, I'm going to put in the dead code allow so we don't get a bunch of noise about this. But what this does is it picks a random speed between 0 and 3 because our max speed is 4. So let's try colors. And I think to do this, we will want an array, the custom style color, and then we're going to want the color type. So we'll take self, we'll take white, green, dark green, dark gray, clear gray. Hey, there is a gray. Let's do that. Okay, and to do that now, we want to bring in another library called lazy static. All right, and lazy static will allow us to declare static, basically constants, and these constants will allow us to allow us to embed structural data instead of just static data. Um, it'll do the calculation beforehand, more or less, and then stuff it in the constant, and then we can pull it out as our program runs. Constants work a little differently. They're just embedded directly into the program when you get into it. So something like lazy static is needed in a language like Rust, which really doesn't hold your hand over this stuff. Oh. Okay, so now we have colors. So now we can do this. We can do colors, and we want to pick a random color. So the easiest way to do this is to take a U size. Now there are traits uh, for the random library that provides some of this functionality, but my experience so far is that this is a lot less work. Just modulo by the random, and then it'll pick it out from there. So it'll always pick the right one. And then we want to pick color. We also need to pick a symbol. So let's see here. Well, how are we going to carry the symbols? Let's think about that. How about a type of corpus equals back of care? All right. This is just our file, right? Let's pick a symbol. Let's pick care. And we'll pick a corpus. Right? And we just need to borrow it. We don't need a copy of it. And here we're going to want to pick corpus. We can do this the exact same way we did this with colors, even though corpuses land very dynamic in comparison. Okay. And finally, one of the things I think we should do is consider how volatile these changes are. So if we're going to be picking these, how often are we going to be picking these, right? So we'll call this pick volatility. And we're going to make this a number, floating point number, between 0 and 1. So random F32, modulo this by 1.0, and we're good. Okay. So Now we need to ingest the corpus. Let's call this get corpus. And at this point, we're going to want to corpus. And we should make this a result, so we're going to do IO. And all right. And since corpus is just a vec, we can call new on it. No problem there. And we're going to need to bring in a couple of other things in the IO package. STDI and a read to end. And we'll call it read C. We'll ignore the U size. So read to end returns the amount of characters it read, or an error. And we want no error to come back, but we don't care how many we read. And let's see here, and then we'll go OKC. And what that will do, oh, it's U8. Okay. Oh, I didn't realize that. So let's dial back. So what we need to do is we need to create a U8 and we need to read it. And now that we've read it, we can map X into, and we can collect that focus, right? And depths aren't iterated by default, so we need to do that. Does that make sense? So we take the vec and we read standard in all the way to the end, which means when standard in closes, this will finally be filled. Then we turn it into an iterator. We run a map function on it, which turns it into the character, because at the end, the corpus is determining that that should be a character inside the vec. Okay. Let's see here. The big thing we got next is how do we represent the data on the screen? Now, I think it's important to acknowledge that the data on the screen and the data that we pick from are two different sets of data, as well as the screen itself. That should be a final third set of data. We're going to take a minute and just pause, and we'll get to the stream in a minute. We'll be back in 5. All right. And with the volatility we talked about. All right. Now let's create an implementation for the cell. And I guess the first thing we should do is import default for cell, right? And we can create a default choice for the cell that it gives us a lot of flexibility later when we want to create new cells, like a lot of them. And we'll go cell new, and we'll go like this. How about that? With P picture. I see. That's a problem. So we can't have a default implementation for this because we take the corpus. I mean, we don't want to copy the corpus everywhere. So that would be a mess. So what we'll do is pub fn new. We'll take what we'll do is we'll take the corpus. No, okay. We'll take in a character, and then we'll randomly generate the rest. And so we got C here. We've got color equals pick color. We've got volatility equals pick volatility, and we have speed pick speed. Right now, if we're going to check what position it's in, we also need a position. Right now, how does that work? Is that two coordinate positions? I think we could go with that. The cross-term library starts at the top left is 0, 0, which is a little different from graphics programs. So they start at the bottom right, like a graph. But the way the terminal works, yeah, it makes more sense. So what we're going to do here is identify a position. So I think the easiest way to do this would be with another struct. We can do a tuple struct, which does width and height. Now, the important annotations we're going to need to make are we're going to need to derive debug and clone. And this is going to be more important later, and we'll probably run into why. But anyway, let's do a position here. And now we have to create a position here. So we need to at least know the width of the terminal, but it would also be good to know the height. So let's go with this. Max position. All right. And then what we'll do down here, we go position, and we'll go max position dot 0. No, it's not gonna work. Okay, we need to define the window dimensions, and we'll get to that later. So right now we're just gonna set this to 0, 0. We're good on that. This syntax error is just a bug in the program. Now we need to mix it up. So we'll need to create another function called iterate. And iterate will take the character and we'll let's see here. We'll take self in a mutable form. What we'll do is we'll transform the character, and then we'll determine if we need to actually change it. So how we'll do that is random 32 modulo 1.0 is greater than the volatility. And what this will do for us is provide a sense of randomness with regards to how things are changed. And we can actually change the volatility at the same time things are changed, so things are more likely to change if, at a different rate of speed, a very seemingly erratic rate of speed. So I guess let's make the first thing. We can do that right here. Okay. Now, if actually, let's feed the corpus. I'll show you why in a minute. So we can do that. Then we can do this. We can pick, and we can do corpus, and we can change the speed. change the uh, oh, um, all right. We also need to actually apply some of these features. So at this point, we would want to change the position based on the speed. So if, so if we got the height and the width, you're going to need to know what the maximum height is. So let's put that in there. Let's put that right there. All right. So if self speed, self position one, because we'll make one the height and zero the width. But self speed equals greater than max height. What we'll do here, and I'll show you how this works later, is we want to get rid of this data segment. And we're going to do that by filtering it. And so returning false here and making this return a bool will tell us that we want to filter it and we don't want it to come back. Else self position dot one self speed. Right? So we are increasing the position and by the speed and then resetting the speed in a minute. So this what will happen is we'll go forward like 4 and then the next time it moves it'll go like 2, right? And if it goes past the end of the screen, it just disappears. Let's see here. So that's our iterate function. And now we clearly are going to need a way to manage the position. And that involves understanding how the dimensions of the window work. A cross term gives us features for this. And let's look at them. So, all right. All right. So let's create a new struct called window. Let's get our derives in there. All right. And the window is going to have cells. It's going to have position, we'll call it dimensions. Probably should have called the type dimensions, but whatever. It's not really dimension, it's just going to reuse. Cells dimensions, and let's see here. We want the corpus. And we want to own it. And we want, yeah, I think that's about it. Let's go into the window, right? And the first thing we need to do is get the terminal dimension. Of fn from terminal. We're going to create a window with these positions, and everything else is going to be default. So, okay, so cells default corpus. I'll get corpus here. And we'll make this a result. Because we're going to need to do that anyways. And we'll leave this alone for now because we're going to call cross term criminal size. Okay. And that's going to also return potentially an error. Right. Now we can do that width, height, and now we can do position, width. Okay. All right. Oh, dimension. Does that work? Yep. Okay, so what we did there is we needed to do some type conversions because a U16 and a U size are technically different types. I don't even think we need the try into because what the try into will do is allow for errors. I think we're good. Yeah. Um, now that we have this, get corpus is going to read from standard in automatically, so this is going to kind of be baked into the functionality. We can do a default for window that does, let me probably make this pub, but the default can just call window from criminal and expect and we know we cannot perform IO, so that's what's going to happen. The program will crash saying, cannot perform IO. At this point, we need to look into kind of like how we're going to run our loop and how we get our cells involved. I think the best thing for the cells is to generate a bunch of them at the beginning. And the easiest way to do that would be, let me think about this. Let's make a function for this, okay? Generate cells. Cell. And we'll go, we'll go there, corpus. All right, so generate cells will be for 0 random size, and we'll modulo this by, let's put this in the window implementation. I think this would be better. We probably want to modulo this by the width, but I mean that sounds really tempting. But then we'll have one on every line, every column, because we want them to fall straight down, right? So I guess what I'm really thinking here is that we start with self dimension 0. I don't know, like divided by 10. And that'll round off. That's fine. That would be reject new. Push. So new. Get pick character. Self corpus. And yeah, I think that's it. And your U size there. Oh, for the max height. So self dimensions 1. and then we return B. Now, the unfortunate problem about this is that we have to do this. Oh, no, we don't want to actually return the cells. We want to set them. So, okay. Yeah, return this at all. Yep. And here, and we don't need this. Yep. So let's do this. W equals window dot generate cells. Okay. Make sense? We're going to generate the cells before we return it. So from terminal, we'll return a blank canvas, but default will actually generate a few cells to begin with. We're going to take a 20-minute break, and we'll come back to this afterwards. Thank you. Ability of the character showing up on the screen. I think at this point, it would be best to create a loop that goes through and uses each one of the cells and moves its position and draws it. Call this function draw loop. And because we're going to need to give this to the main function, I think we're going to want to expose it. And it's going to be mutable. And let's see, what else do we need to take? I guess nothing, huh? Probably return a result. And let's walk through each cell. For each cell, we want to go through and determine it should be kept, right? So let's create a new set of cells. New cells. Okay. And iterate takes, what does iterate take again? Corpus. Self-corpus. If self-iterate, self-corpus, we want to put that right in new cells. And then at the end of this, we want to cells equals new cells. And the reason we're going to do this way is so we can actually okay, fine. There's just silliness going on here. But cell equals cell dot phone, and then we just need to do this. So this allows us to get a copy of the cell and mutate it and then push it into the new cells. And what that will do is when we overwrite the old cells with the new cells, they'll have the new positions, etc. At this point, however, you need to draw. So we haven't done that yet. So let's bring in standard out and use some other cross-term traits. Let me look them up really quick. And we don't really need too much here. Just can set foreground color because we're not going to use a background color, but we need this trait called executable command. And what this does is decorate all the all the I/O with cross-term functions, which are really handy. So now we need to go through the cells and we need to scan it out, execute. You see how it comes from executable command there. You see right there. And then we're going to give it some commands. Move to, and let's look at the cell, position 0, cell position 1, right? And then we're going to go foreground color, and we're going to set that to the cell color, right? And then we're going to go print, and we're going to set that to the cell C. Let's see how that works out for us. Okay. Okay, so execute. Right. Did something wrong here. And let me look it up. This is what it is. Okay, I see. All right. Execute. Execute. So fundamentally, this method needs to be changed. And here we go. See how these chain together? And then we've got this one, which didn't have a parenthesis on it, and oh, now we need to do the try intos, right? Because we messed with the U size, and now we're dealing with U16 again, which is what crossover wants to do. Okay. So what this is going to do is when it's invoked for every cell, it's going to write out the current position and the current, stuff, and then it's going to try to iterate it. If it iterates successfully, it's going to push it back into the new cells for another iteration. Otherwise, it's never going to make it back there, and then it's going to overwrite the cells. Okay. Now this should all run at this point. The disadvantage to this program is that it is very fast at this point. It's going to run as fast as a computer can push it. So what we're going to do is get this into tomatrix. I'm just taking star here because there's no point in doing anything else. Let w equals window.default draw loop. Okay, so we're going to go loop, draw loop. We're going to question mark that, and then we're going to do standard thread sleep, and that's going to allow us to sleep for duration, and we're going to sleep for 1 second. Oh, I got that wrong. All right, so let's try our run. Nothing. That's not good. Oh, we didn't take any input. We still got nothing. What's going on here? Something's going on the screen. You can see it. It's just really slow. Look at that. You can see it on the screen. And we never cleared the screen, so let's do that now. We can do that with cross term. And we can use file clear, cursor clear. Let's see what we got. I think TTY will cover this. No, I'm stupid. All right, let's try terminal. Clear. I think we need clear type too. All right, and we can get each standard standard out. And then what we need to do here is stand it out, execute, execute, and we clear 35 all. Okay, and I think we're good there. So let's see it. Yeah, you can see it. It's drawing very, very slowly. It's also drawing only in the first column. Why is that? That seems strange. Okay. So what I wonder is if we got the window dimensions wrong. Like this is height and this is width. Right? So we got everything else lined up. So let's see what happens here. Something is off. So let's figure this out and see where this happens. This is curious. Oh, we never set the position properly. So what we can do here to make this easier for us is we can change this to a window. And actually, we don't really need to do that. We just need to pass the window here. And then window, we set 0 here, and window dimension 0 is our maximum width. So we can set random view size. We can do that and get a random position over the width of the function. And then we can use window the dimensions.1 here for the max height. Well, max height, right? There, we should be good now. Let's just stay. Further a bit. Let's see what happens. Aha. And we'll just pass self in instead of doing that. All right. Let's see what happens now. Oh, there we go. We got some stuff on the screen. So let's make it a lot faster, okay? Let's make that. Let's try that. There you go. We got some things there, but there's not too much variance, right? And we never got any new characters on the screen. So in the draw loop, let's do this. Let's go for in 0 random view size. My self dimensions 0. We could probably turn this into a function because we used it earlier. And oh, we can just do that. It is a function. Oh. All right. So if we make generate cells, just return back a cell. So assigning it, and we make this up here, w.cells equals generate cells. I think it's good. And then what we could do down here is just new cells append mute generate cells. Go on. So generate cells. And now we have more characters. Yeah, so you can see how much that affected it. We clearly don't want to add that many characters, but the reality is we're not adding any white space. You can see the white space is all coming from the actual output. So let's do this. Let's do this instead. So if in random in the character picker, we can do this. View size, and we'll modulo it by 5. And if it equals 0, we'll pick a character. Else, we're gonna give him back an empty character. Let's try that out. See how that works. Look at that. That's pretty awesome. So now we have an issue where all the characters fall at the same speed. And they're also falling very, very fast. Which is not a problem. This is kind of an artifact of how long it took. So we can do this and increase it a little bit. And then it's still, right, it's not falling in the way we want it to, honestly. Falling at a constant rate of speed. All the characters follow. Everything, nothing is very slow. So let's do this. Let's chop this down to 1. Okay, and let's see what happens now. Okay, that's way too slow, right? So let's give it a big ass number. And you can see it's starting to fill in. But it's more like a random fill. It's not, you see, it's not like falling. So let's do this. It's very obvious that our character picker is a little too violent because it's picking different characters every time. And we should probably temper that a little bit. And random, right? And we can do bool here. And we'll just get a random, right? That's getting a little better. You can see that. You can see that. Right. Also, you can see that scrolling too. That's not good. So we'll need to fix that. The speed is going to take a little bit more effort. So what we'll do is we'll sleep for a random period of time. 0, and then what we'll do is we'll do random view size modulo 100,000, and then we'll multiply, and then we'll add like 10 million to it. So they'll fall at a predictable rate of speed, but not a very high rate of speed. Oh, okay, you put. Oh, right. Okay. Now we're starting to see an effect, right? You can see it. I'll start it over. And you can see that the characters are falling, right? Not doing it very well, but they are falling, right? And they're falling at surprising rates of speed. So what we really need to do now is slow this down a little bit. So let's add some more zeros. Okay, that's still way too fast. So let's add some more zeros. All right, that's too slow. All right. Okay, we're getting somewhere. Now I would say the chance for picking a character that's not white space is actually too low. Let's turn this number down. Let's turn this number down to 2. See what happens. Oh, let's turn this number up. Let's do this. Revert this and make this like 5. See what happens. There we go. We're getting close. It is drawing an awful lot. You can see the cursors. And it's pushing the screen up. You can see that too. So let's figure out why that is. That's probably it right here. It's not by 1 error. Looks like we're on the right path. It's not pushing the screen up anymore when it reaches the bottom. Ah, there's a bug. Okay. Let's figure out how we got there. Let's see if we got another off by 1. Yeah, it looks like it. You can see now the bottom line is cut off, which is keeping it from scrolling. And now we have another problem, which there are clearly way too many characters on the screen now. So let's play with this number a little bit. Let's go 3 here. Let's see how that works out. I mean, this could be a lot more complicated, as you can probably expect, but we're getting somewhere really close. And it's not bad. It's just not perfect, right? Let's do this. Let's make it fall a little faster, okay? It's a nice effect. I think we should be a little less random with our character picking. So we'll go U size here, and we'll go modulate 10 equals 0. Okay, we'll be much more likely to pick our original character. And you can see that. The Z is falling all the way down, the R is falling all the way down. So now we have a pretty awesome little stupid program, right? We can do a lot with it at this point. You know, we can make it clear the screen or change the volatility, or we could, you know, when the screen changes, it could start over, or it could pick a time to give up and start over. I mean, there's a lot we could do here. And as you can see, the cursor is going nuts. So, you know, we could make some optimizations there. I mean, let's see what it looks like, right? It's actually using 0.2% CPU. It actually uses a lot less than the original version. So how about that? Yeah, that's the majority of our show. I hope you liked it. I'll put this code up online when I post the videos, so you can see how it was formed. But if you want to look at a similar version, the URL is in the first chapter of this series. We'll have that also in the recorded video. The streams will be gone after the video is posted and edited. So pay attention to my streams. I'll be doing more of these soon. I'll be bringing things like load balancers and CI systems and all sorts of stuff, which it takes a little more advanced click to show you how this works. I think technical education is the most important thing we can do at this time in our lives, with the way society is going. And I hope you can join me for my journey. Thank you. My name has been Eric Hollinsby, and this has been the Scarlett School. Have a good day.